In this video, I'm going to talk about phase angle as it applies to simple harmonic motion. Please read the success criteria for what I plan to cover. Let's talk about phase angle. First of all, I have a sine curve here. So here's x, here's t. And I've graphed this equation, which means my amplitude here will be x naught. The value written in front of the sine is the amplitude. Now this is our angular frequency. And from my other videos, you should know that that is 2 pi over the period, or 2 pi times the frequency. On this graph, I'm sure your math teacher has told you that after one complete sine curve, we should be here at 2 pi radian. That's why the value in front of t, and t is on the x-axis, gives us angular frequency. Now, your teacher might have taught you about the unit circle, making this pi, pi by 2, 3 pi by 2. And it's telling you where you are along this sine curve. Well, that's what we're referring to as its phase angle. So for this particular equation, you can see that my crest here is going to be at the phase angle of pi by 2. We typically break our sine curve into these 4 pieces. Now, why does that become important for physics? Well, I've got 2 different sine curves here now. So what does this mean for physics? Well, you see here I have 2 different sinusoidal curves. This is my red one, and this is the blue one. Notice here, I now have something inside these brackets along with my omega t. What that's doing, since it's inside the bracket, is moving it left to right. And how much did it shift? It shifted pi by 2. Notice my pi by 2 would have been here, and now it's moved in this direction. In the equation, it is plus pi by 2, but notice it's shifted to the left, so we'd say the phase difference is minus pi by 2. It is actually behind in terms of time. Notice if I was referring to the blue one, I would have to the next peak, I would move in this direction. I could have also, compared to the red, I could have done one that had a phase difference of pi. It would have looked like this. And if you've already done the motion graphs for simple harmonic motion, you would know that if the displacement time graph looked like this, our acceleration time graph looks like the yellow one. They're actually a phase difference of pi. So let's do an example. I've got 2 objects here, both undergoing simple harmonic motion. It asks me to state one measurement that's the same for each object and one thing that's different. Well, first of all, one thing that's different is the amplitude. And one thing that's same is the period. Take a look. From 100 to 450, or from 0 to 350. They will have the same period. And I'm assuming this is time right here. Determine the phase difference between the 2 waves. In order to determine the phase difference between the 2, we need to compare when they're at a peak compared to the others. When this one's at a peak, this one's just crossing, so they're going to be 1/4 of this oscillation out, and that's going to be pi by 2. Typically in IB, our answers are going to be either pi by 2 or pi. Please read the success criteria one more time, and I hope you can say yes to all those bullet points.